springing up all over the country from completely unrelated points, and all at about the same time. It all concerns how we think of the emitter to base junction of our standard transistor, our little crystalline device that seems to be giving us a bad time when we start trying to figure out H parameters and things like that. The concept of the single junction in this device doesn't seem to be quite enough. Most of the texts that teach us our H parameters on transistors mention the possibility of another parameter, one that we're very used to incidentally. The cathode impedance of a vacuum tube is its counterpart. And for lack of a better word for this actual gadget, or whatever it is that exists between the base and the emitter of this device, I am going to call it the reciprocal of the vacuum tube's GM. Now, GM, of course, is measured in transconductance. So I am, for the purpose of this film at least, going to call this, in relation to the transistor, transresistance, the reciprocal of conductance. Now, it's true, we do have a diode in here, but it's not just a single diode. Let me illustrate a little better what I mean. This, perhaps, is the most prosaic presentation of the transistor, where we have the emitter, base, and collector shown in boxes. This is the concept of the emitter junction and the collector junction, and yet it's not quite true, because we can't put two diodes together and have them work like a transistor like this. In actuality, we will have an extra connection between these two sections of our equivalent double junction action of the transistor. This action of the transistor really says that I will be having a short circuit between a part of this diode and this one, and yet still have the connection from here to here operate to a limited basis. Well, this limited basis could be drawn in terms of just this one junction, and is in the equation for the conversion of the H parameter high to Hib. But let's illustrate this a little further along, too. The actual diode picture that I would like to present to you looks something like this, where our base emitter junction would operate to a very limited degree with tenths of volts, calling for very small amounts of current to the actual base connection from the emitter, and yet at the same time would release a greater amount of current to the collector junction. Note I said at the same time, because this, as I've said, not only draws current to the base, but I have a short circuit current that goes to the collector. This means I have a lower resistance than what I would have in this junction alone. I don't just have that one tangent to the base emitter curve that I might have if I were operating at this point in my curve. I have it in parallel with some resistance that reacts like this. It's very convenient to show this on the 575. So why don't we illustrate this with the instrument here on my right. Let me step around to the other side of it. Here is our curve tracer, a very special type of oscilloscope. I plug the transistor and turn up the voltage, and the instrument, of course, will draw for us the active output curves of the device. The 575 draws these curves for us with current in the vertical axis and collector to emitter voltage in the horizontal axis for us here. These actually are the collector curves of the device, and they're not the only set of curves this instrument can draw for us. We can see the actual graph of transresistance, for instance, simply by changing the terms of the horizontal axis. We already have the current axis in the vertical here. Let's switch the vertical to base emitter volts this time and set it to a sensitivity to show us an actual variation of impedance. Here we are. This is the shape of transresistance seen from the emitter relative to current through the active device. If, for instance, I was operating at this point, a tangent to the curve at that point, of course, would be the effective AC impedance. However, if I was operating up here at this point, I would have a completely different AC impedance, a much, much lower impedance than down here. This, of course, is exactly what the formula for transresistance tells us, 26 over the level of current through the junction, IE, plus a little fudge factor. Transresistance, a very useful device. Let us refer to the mathematics of the situation very shortly here, since most textbooks do mention it. The one primarily that I have reference to, or the equation I primarily have reference to, is the one that states that the GM of a transistor is equal to Q over KT. Quantity of electrons at a given temperature divided by a constant. Now, this is not the whole formula. It is the general reaction of the whole formula, however. In general, this would give us the slope of the ideal perfect crystalline diode curve at any level of current. Now, admitted, transistors are not perfect, but resistances and other parts aren't perfect either. And if we are going to use imperfect parts, we can be allowed to use imperfect equations as well. 1 over GM with vacuum tubes is called ZK. Well, this then could readily be equal to KT over Q, merely taking the reciprocal of each half of this equation. If we wish to follow it further, we can note that the quantity here is representing electron flow per unit time, which is current, and our 1 over GM characteristic, or our transresistance, R sub TR characteristic of the transistor, is equal to some constant divided by emitter current. The constant, Joyce and Clark tells us, is 0.026. In other words, we have the statement that 0.026 divided by emitter current represents an impedance, a resistance, if you will. It won't represent much resistance. It can only represent, under most conditions, a fairly small resistance. And please remember, it is not only Joyce and Clark that says 0.026, because there are numerous other texts as well. Semiconductor circuit analysis by Cutler lists 0.026 over IE as the resistance seen when you view the transistor from the emitter's vantage point. Numerous other texts refer to it. Men in England, engineers there, are also plugging this same idea of viewing this emitter impedance, if you will, and predicting it on the basis of 0.026 divided by IE. Transresistance. Let's switch back and see now how this simplifies our concept of the transistor as a whole. The graph that I showed you before of the two diodes looked like this. A high impedance here at some operating point and a low impedance here. The collector junction, if you will, carrying the beta times emitter and base current, which represents this impedance here. Perhaps it would be better if we viewed this as a single resistor within the transistor. Let's take off some of these and redraw the picture. If the picture looked like this, we would have a single resistor that we call transresistance connected to the emitter. There would be a group of resistors, you might say, or one resistor segmented vertically into a series of, or a whole group of parallel resistors possibly, only one of which would be connected to the base. That's the base lead there. It takes its own little share of current from ground up through this resistor and on out the base connection. But if beta is to be correct, through the beta other resistors I will have in parallel with this, all giving us the composite value of resistance that our formula shows us is true, transresistance, I will have beta times the value of this one resistor as a conductance, literally, because parallel resistance takes the value of 1 and divides it by beta, doesn't it? All right, then I will in effect have the H parameter high divided by beta plus 1 for the total resistance. Well, beta plus 1 is the conversion factor for the H parameters high and Hib. So we certainly are not disobeying the H parameter concept by utilizing this concept. For 1 unit of base current, I will have beta units of current coming through these other parallel resistors, all going to the collector. Now note what this says. This says I will apply a voltage from base to emitter, or apply a current flow from base to emitter, and through this one resistor with the voltage required to develop that current, I will develop predominantly a current that will go to the collector load. This says I have a series resistor to the load resistor, and I will have a voltage on the output directly related to the ratio of this resistance to this one. Yes, voltage gain for a transistor will equal RL divided by transresistance if its RP effectively is high enough. Now, transistors don't have infinite RPs any more than pentodes have infinite RPs. Pentodes actually will have a higher RP than transistors. However, our transistor curves may readily, in the collector circuit, look something like this. We might find that for a certain set of curves, we would have a slope similar to this. I've shown one with 15 volts across the device here, and the capability of a pretty husky amount of current, 30 mils, if you will, in the vertical direction. This shows that for a 4 mil change here, I would have an approximate 12.5 volts change in the horizontal direction, or an effective RP a little in excess of 3K, about 3.1K to be exact. Well, a 3.1K plate load working into a 500 ohm resistance, which represents this load line, isn't going to affect it too greatly. So even on a general rule of thumb basis, we can get a prediction of the voltage gain of this device somewhere in here, relative to, say, transresistance divided into a 500 ohm load. This line representing the 500 ohm load line with a collector voltage VCC of 15 volts. The gain then, at one point, would be much lower than some gain further up. Yes, this is very true. Referring once more to your transistor collector curves. Do you remember what they looked like when they were voltage driven? Well, let's step once more to the 575 and view the collector curves of a transistor under voltage-driven conditions. If I drive with voltage, I get this effect. Now, note, in the vertical direction here, I can bring things down or stretch them up, as the case may be, but each step up I go in voltage, I step a higher amount of current. It's anything but linear, which is just exactly what our gain factor is, anything but linear over the total range of operation. But if I use this as a small signal characteristic, I will have the gain of the operating point I predict. And the operating point, remember, is predicted by the level of emitter current divided into 0.026. Now, true. Once more to the blackboard. We cannot make perfect transistors. Since we cannot make perfect transistors, we cannot accept the full equation for the perfect crystalline device that physics tells us ought to be true. We have to add a fudge factor, if you will. So, to our basic story over here of R sub TR equal to 26 over IE in milliamps this time. I'll incorporate the power of 10 in the denominator. We have to add this fudge factor of what we will call REB. A little extra resistance between the emitter and base that accounts for the resistance of the connection wire, the solder connection of lead to semiconductor material, the imperfection of semiconductor material, since we're not perfect, and usually we find on a rule of thumb basis we can add something between 3 and 5 ohms here and come out with a fairly accurate result in our actual computations. If, for instance, our transistor were operating at 2 mils, we would have an R sub TR then equal to 26 divided by 2 plus something between 3 and 5. Well, that gives us 13, doesn't it? Well, let's call it a total with REB then of, well, maybe 16 ohms if we only add 3. Or if we add 5 to this, it will be 18 ohms. It really doesn't make too much difference which way we use it, because the value of the resistor you're dividing it into 9 times out of 10 will not be accurate within 10%. And this will either way be just about as close to the 8-parameter Hib as you will measure the device on almost any piece of equipment. This tells us then that we can go along with vacuum tube theory, that the gain of the transistor, AV, voltage gain that is equal to GM-RO. If you will, the reciprocal of GM, then if I'm going to use 1 over GM, I'm going to have to divide by it. It equals RO over 1 over GM, or R sub TR. RO, if the effective slope of the collector curves is steep enough with relation to the load line that you have to consider the two in parallel, will be the parallel combination of the two, but 9 times out of 10, it will simply be the load resistor. It goes along with the vacuum tube theory. Remember, AV equals GM-RO for a pentode. Only instead of saying RO, we usually say RL. In triodes, we use the same formula, GM-RO. Only with triodes, RP is quite low, and we find that we have to say GM times the product over the sum. RP times RL over RP plus RL. And then we change the formula once more by replacing GMRP with the factor mu, the triode gain formula. Yes, I mean exactly what I'm saying. Transistors can be computed and figured in the same fashion as vacuum tubes. The voltage gain of a transistor amplifier follows exactly the theory of a vacuum tube amplifier. GM-RO. Only we don't use GM, we use R sub TR, transresistance. We can multiply it by beta and say this is the input resistance when we view it from the base. We can use it as the resistance over which E-in is applied to develop a signal current which goes to RL and develops our output voltage. As I said, a concept that most textbooks admit and point out but fail to follow up. And it's springing up all over the country as a simpler means of transistor amplifier analysis. A rule of thumb approach, if you will, to transistors where you don't need the manufacturer's specification sheet under your thumb in order to predict what will happen. A means by which we can figure all transistors in the same fashion for gain purposes and understand that this is a mid-frequency range of gain, and if we need something that's far out, well, we're going to have to go to a transistor that's far out to get it to work in that area, that's all. But on mid-frequency operation, they'll all work the same and can be all figured the same. This formula is a little more true of germanium transistors than it is of silicon transistors, but frankly, I've found it works just about as well regardless of which type is going to be in the circuit. It predicts on a rule of thumb basis what I want to know plenty close enough for me to go ahead and build it. I hope it helps you as much as it has me.